Hello, calculus students. We're going to do a relatively, or hopefully, short little lesson here talking about properties of vectors. We've got a whole bunch of properties, and so you'll probably want to pause this next slide coming up and maybe take some notes or at least sort of read through it so that you feel comfortable with it. Um, so we've moved on to three-dimensional vectors. We know that there's three components now, x, y, and z. X again moving forward and backwards, y moving left and right, and z moving vertically. We know that vectors can be equal, and if they're equal, every one of their components are equal. And that's what we're seeing over here, where if you have vector A and B equal, then all their components like A1 and B1 have to be equal, A2 and B2, and that's what's sort of expressed right here. Every component has to be equal, just like on 2D vectors. Vector operations, if we have two vectors, we can add them. You take all your x components and you add the x's together, the y's together, the z's together, and that's shown right here. Same idea for subtraction. So same thing that we did for two-dimensional vectors, and as far as adding and subtracting goes, it's just like matrices, I suppose. Then we can do scalar multiplication once again, which feels a lot like distribution. If you have some number k multiplying a vector a, you can essentially distribute that k to each and every one of the components as shown here. And then we have a few other properties of vectors, and these work for 2D or 3D vectors. Again, when you've got parallel vectors, there's some scalar that you can multiply by 1 to make it into the other. We see magnitude happening there. They talk a little about opposite vectors. If you have a vector and its opposite, you add them together and you get nothing, or the origin as a position vector. Adding vectors is commutative, meaning you can go in both directions. It's associative. And if you add on a vector of 0, 0, or in 3 dimensions, 0, 0, 0, it's an identity. We can't do division of vectors. And when we do multiplication, we have to specify whether it's dot product or some other product that you may study at a later point. All right. So all I'm going to do here for the rest of the lesson is just run through just a couple different book examples showing off some of these properties and a few other techniques we can use when dealing with vectors. So in this one, we've got vector A given in component form is -1, 3, and 2. Again, it's a 3D vector with 3 components. And then we've got this statement here, find what looks like absolute values, but we know that means magnitude, so find the magnitude of 2A. Well, 2 is already a scalar, so its magnitude is 2. A, we need to find the magnitude, so let's start with that. We're going to take the magnitude of A, which then would be equal to -1 squared plus 3 squared and 2 squared. That becomes 1 plus 9 plus 4, which is the square root of 14, and that's equal to the magnitude of vector A. But I want double that. So if I multiply this by 2, I just multiply that by 2 as well. And voila, there is our answer. We could have done this another way. We could have also distributed the 2 at the beginning, and then you would have had all of this stuff in here double. So you'd have -2 squared and 6 squared and 4 squared. But it would end up reducing, and I just saved us some trouble by leaving the multiplication till the end. Here's one dealing with 3-dimensional vectors and parallelism. We want to find the components R and S given that vector A is parallel to B. Well, the 2 and the S, I know there's some scalar that I can multiply by to turn the 2 into the S, but I don't know what that is. But if I look at the second component here, the Y components, I have to think, how could I turn a -1 into a 2? If you're unsure, just divide. 2 divided by -1 turns into a -2. So I know that my scalar or constant is -2. And if I multiply a -2 by any of the components here, they should turn into my B components. So let's try it. If I take -2 times, actually, let's rewrite it this way. So let's say if I've got K times 2 -1 R, that should turn into vector B. Therefore, I know that my negative 2 times 2, negative 1, and r should turn into my b vector, which is going to be negative 4 and positive 2, and then 2r. Well, by doing that, I figured out 2 of them already, so I know that s has to be negative 4. So I've got my s already. I've confirmed the correct answer here with the negative 1 turning into the 2 after multiplying by the negative 2. And then, unfortunately, I'm going to have to go the other direction. So if I've got this 3, 2 times r should, I'm sorry, negative 2 times the r should equal the negative 3. I can either go the other direction and divide, or I can just turn it into an algebra problem and say that I know that, sorry, that should have been a negative 2 there. Negative 2r equals negative 3. Divide both sides by negative 2. And so I get r equals 3 halves. So s equals negative 4, r equals 3 halves. Not my best explanation, but I think we got the job done. And we'll do one last example here. I like this one because it's a little bit more challenging. We've got vector b. It has a length of 7, in the opposite direction to vector a, which is right here. So let's start with the opposite idea. So the opposite of a, I just distribute a negative 1 to each and every one of these components. So that's going to be negative 2 there, positive 1, and negative 1. Just multiplied everything by a scalar of negative 1. Now I need to make it equal to 7. So I'm going to figure out how long this thing is. I could use either one of these vectors because they're the same length. They just go in different directions. I'll use my new vector, and we'll do magnitude. That's length. So I've got negative 2 squared plus 1 squared plus negative 1 squared. And that would be my magnitude. I'm going to get 4 plus 1, which is the square root of 6. The square root of 6 is not 7. It's not 1 either. It's not a unit vector. In fact, it's square root of 6 times too big in order to make it a unit vector. So if I were to divide by square root of 6, that would make it a unit vector. But a unit vector is not a 7-unit vector. It's just a 1 unit. So then I would need to multiply by 7. So the scalar that I'm going to use is 7 over square root of 6, and I'll just multiply by that by everything over here in my negative a vector. So I'll end up with 2 times 7, or negative 2 times 7, which is negative 14 over square root 6. And if you want to rationalize your denominator, that's fine. And then 7 over square root of 6 times 1 would just be 7 over square root 6. And the negative 1 will be negative 7 over radical 6, all as my vector. And that would be opposite direction and have a length of 7. Also known as vector b. Handful of problems on 2 different pages here in the book, page 300 and page 307. Take a look at those, and we will see you next class.